Alright, so in this next video I want to answer these questions about carbohydrates. It's about carbohydrates, but it's also about condensation hydrolysis reactions. So I'm going to try to kind of go a little quickly, but I hope to show you a couple of kind of cool things. So the first question here is about when adding bonds on molecular diagrams of carbs, does it matter if the atoms are inside or outside of the ring since they're three-dimensional? That's a great question. The models that were in the previous videos were two-dimensional drawings, but I want to show you this program. You guys are going to get familiar with this kind of program. This is called JMOL, and this allows me to use three-dimensional visualization software to look at this molecule. This is glucose, so let's count up and make sure we understand that C6H12O6. Our carbons are gray here, so we've got 1, 2, 3, 4, 5, 6. 6 carbons. Our hydrogens are, our oxygens, hydrogens are next. So hydrogens are white. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we've got 6, we should have 6 red oxygens. 1, 2, 3, 4, 5, 6. And this should match your color coding that you took in notes in a workshop way back. But you can actually spin this around, right? So you might have seen that ring, but here's the ring. So here's that ring. And the question's about the direction that the H and the OH go. So let's say for this carbon right here, this is the oxygen here, so this is labeled carbon 1. This is carbon 2, 3, 4, 5, and 6. But carbon 1, let's say, has a hydrogen shooting off this way, and an OH going in the opposite direction. OH is over here. OH is over here, and then hydrogen over here, OH over there, and hydrogen pointed backwards. What I want you to notice that it's really a space issue, right? So these atoms are not to any kind of scale. But remember that each of these atoms have their own electrons floating around them. They're also being shared, and these electrons are going to repel against each other. So wherever there's more electrons, they're going to repel against other locations with lots of electrons. Which kind of goes to another question that's being asked here. Why is the hydroxyl group polar? Well, the hydroxyl group, just to remind you, is the OH, right? So it's this O connected to this hydrogen, this oxygen and hydrogen. That's a hydroxyl group, and just like in water, this oxygen has a higher electronegativity. It's got and therefore attracts more electrons, and therefore if you wanted to put a little negative symbol over here next to this oxygen, you could have one of those. It's a negative charge. Well, that negative charge is going to be attracted to and create a hydrogen bond with water molecules. So that polarity, that negative charge, because of this electronegativity of the oxygen, will bind with water. So it's got its own polarity to it, and it's hydrophilic because it bonds with water. And that's why when you add sugars, which have a lot of these hydroxyl groups, they will dissolve in water until there are no more hydrogen bonds to be made, and then we say that solution has become super saturated. Okay, and I hope that's a term that you remember from middle school. So let me go back to my questions here. So it does matter what direction they're going to be in because there are more electrons. So let me do a couple of little changes here. So I'm going to move my console off to the side here. So if I select carbon and space fill that to 1.0, select oxygen, space fill that to 0.75, and these are just estimates of the atomic radii or the atomic diameters, right? These are really diameters. And select hydrogen and space fill that to 0.5. We can see now that if this OH was pointed, it is pointed this direction. If this OH would spun around and was over here, it'd be awfully close to that OH, right? And that's that's important to make sure that you understand that this is going to be evenly spaced out in reality, right? In your drawing, it's going to be difficult to do that, to showcase that, because you're only working in 2 dimensions. There was another question about, is it OH or HO? And it depends on the orientation that you're looking at this model. So let's look at, if we're looking at this carbon, this carbon, this carbon, we would write this as an O and an H. So it would look like on paper as HO connected to a carbon. It's the oxygen that can create 2 covalent bonds, and hydrogen can only make 1 covalent bond. So this oxygen has 1 covalent bond to the carbon and the other covalent bond to the other hydrogen. Over here, this oxygen is covalent bond to that carbon. Well, so here it would be O and then H. So HO, OH. The O is critically important, that the O comes between the carbon and the hydrogen, because that's what's making the bond. If you had carbon and then hydrogen and then oxygen, well, that's an impossibility, because hydrogen can only make 1 covalent bond. Okay? It only has 1 valence electron, and if you're thinking back to your shell model, the inner shell holds 2 electrons, so it only needs 1 more. It's going to create 1 covalent bond. So we answered the first 3 questions there. So why is the C1H2O1 ratio only for monosaccharides? All right, let me go back to my screen here. So when we're talking about, let's say we're taking 2 glucose molecules. Let's call them C6H12O6 plus another C6H12O6. I hope you understand that this is just a different representation of this, right? So this is a different representation. It's going to take some kind of enzyme, which there's another video on, and it's going to take some kind of enzyme to do this, and it's going to end up with a disaccharide, right? So this is a monosaccharide, monosaccharide, and then it gets combined to make a disaccharide. So this disaccharide is going to have 12 carbons. You would imagine, if we're just adding, right, we would have a balanced equation, you'd expect 24 hydrogens and 12 oxygens. And that fits our 1:2:1 ratio. But if you review your notes on condensation reactions, you'll know that water, H2O, comes out. So we have to end up with water in order for the ends to stick together. Well, if that's the case, then 2 hydrogens have been removed. So we don't end up with 24, we end up with 22 hydrogens. Excuse me. And we don't have 12 oxygens, we only have 11. And this is our formula for a disaccharide. Now you should, for a particular disaccharide, C12H22O11. And so what you notice is that it does not fit the carbon hydrogen oxygen ratio of 1:2:1 because water is removed, right? So water has been removed, but what you should note is that your hydrogens and oxygens here have a 2:1 ratio, and they also have a 2:1 ratio here. So this ratio of carbon, hydrogen, and oxygen, 1:2:1, continues to get worse or further off as you add more monosaccharides, but we always end with we always have a 2:1 ratio for hydrogens and oxygens. And that's key because that's not true for lipids, but it is true for carbohydrates, okay? Let's go back to the questions. If I can get to them. Okay. Do condensation and hydrolysis reactions work with all the macromolecules? Yes. So condensation reactions again are when So I'm going to do a little T-chart here. So condensation reactions go by lots of other names like polymerization reactions, synthesis reactions, dehydration reactions, or even anabolism. Okay? But the bottom line is that we're building larger molecules and removing water. But a hydrolysis reaction, it's a catabolic reaction, and this is breaking down large molecules and it uses water. So water needs to be a reactant here, and it's a product in the condensation reactions. Okay? But that's true for carbs, lipids, and proteins, okay? And then this last question about dimers, and I know this HX thing is a little strange, so it's just because I couldn't write it very well. So in a previous video, I'd given you something like this. And this is the key here, is that all that this molecule has done is flipped around. So this is, oh, excuse me, I made the mistake that I told you not to make. So it should HO. Okay? Because the oxygen is what binds to this carbon-based circle. It's just, it's like in algebra when you have a variable, right? So this could represent a monosaccharide, it could represent an amino acid, it could represent a fatty acid, but it's just a placeholder, right? It's like the letter X. It's just holding the place, but we've got two ends to it, right? We've got a carboxyl group, the OH, and we've got a hydrogen on one side. And this one's just kind of flipped 180 degrees. But when we put them together and we use an enzyme to do that, we will take the OH off of one side and the hydrogen from the other side and combine that. We've got H2O. And what we end up with would be something like hydrogen with this placeholder, an oxygen, a placeholder, and hydrogen, plus the water that came from this H and this OH, right? And that's a condensation reaction. We made something bigger, and water is one of our products, okay? I hope that helps, and that answers all those carb questions, and then the next one we make is about lipids.